Hello again, grade 7s, and welcome to the final unit of study in grade 7 science on plants for food and fiber. I'm only going to do 3 PowerPoint lectures for this unit. The unit does have a lot of content, but I'm really just going to try to focus in on like 3 key concepts, as I feel as though these are the 3 most important concepts that you need to take moving forward. So today we're going to talk how water transports in a plant. Learning outcome is to describe the processes of diffusion, osmosis, conduction of fluids, and transpiration, specifically in plants. Okay, so let's first of all define what diffusion is. Diffusion is the movement of molecules from an area of high concentration to an area of low concentration. Okay, I'm just going to try to illustrate this. We'll look at a different picture in a moment too. All right, so let's say we have 2 areas. We can think of them like as the 2 areas like 2 classrooms, kind of like side by sides. We'll say that this is like classroom 1. This box here, and I'll put a little dashed line kind of showing a border between them. So I'll say this is like classroom number 1. And then we'll do a second classroom just right beside this one. We'll say it's the same size. And then we've got classroom number 2. Now, within these classrooms, I'm going to show just a few like little circles that's going to represent the number of, let's say, students that are inside the classroom. So let's say in classroom number 1, we have 1, 2, 3, 4, 5, 6. 6 students in that classroom. And then classroom number 2, we have 1, 2 students. Okay. Now, let's pretend that so I said the movement of molecules from an area of high concentration to an area of low concentration. So we're just going to use the students, pretend the students are like molecules. So use that as an analogy. Okay, so I have these 2 areas, these 2 classrooms. One area has more students in it. So I would call it the area of higher concentration. And then this other classroom only has 2 students. So it's the area of lower concentration. Diffusion is going to be the movement of your molecules from an area that has a high concentration to an area of low concentration. So you always go from high to low. Okay, so some of these students are just going to go into classroom number 2. Now, if you're wondering why this happens, like why do you go from an area of high concentration to low concentration? Well, think about it in terms of particle motion. So if we look at these particles here, and let's say that they're just like vibrating and moving around. If there's an area of high concentration and like these students are really, really energetic, okay, they might be like bumping into each other, bumping into each other, bumping into each other. Okay, there's lots of like collisions between the different students, assuming they drank like 50 Slurpees or something like that. Don't drink 50 Slurpees, by the way. Okay, so they're really energetic because they're in close proximity. They're vibrating, they're buzzing around, they bump into each other. And just naturally what's going to happen is because of all these collisions, some of them are going to get bumped into the next room. Okay, you're going to get knocked into this room. As we're in this room, because there's so much space between the students, even if they had lots of energy, it's unlikely they're actually going to bump into each other. So that's why we always go from an area of high concentration to low concentration. Now, this is going to happen where molecules will go from an area of high to low concentration until you have an equal number at the end. Okay, so if we go back to this picture at the top, so we know that some of these molecules are going to go from an area of high to low concentration, and then how much would be in each classroom at the end of the day? Well, there needs to be an even distribution if we're talking about equal sizes of the classrooms. So let's just try to think about this logically. Okay, so I have 6 in one room, 2 in another one. The total number of students in both rooms would be 8. So if I took the total number and evenly divided them, how much would be in each room? Well, you should be telling me it's 4. Therefore, what's going to happen is two of these guys are going to go into the other room. So let's take just this one, and we'll take that one. So those two guys move from an area of high to low concentration. And then I would then have 1, 2 more in this room, 2 less in that one, and then you have this even distribution of 4 and 4. Okay, so that's what diffusion is, the movement of molecules from a high to low concentration area, and it'll keep happening until there's an even distribution at the end. Again, that is assuming that the two areas we're looking at are the same volume. There's the same amount of space in each of them. Okay, let's look at another example. This is for a cell. So instead of looking at using like students as an analogy, now we're actually going to use like real molecules. So we're going to look at O2, which is oxygen molecules, and CO2 molecules. Okay, let's just focus on the O2 molecules right now. So I'm just going to highlight them. So O2, so we got 1, 2. So we have 2 O2 molecules inside of this border right here. So this border represents like a cell. And we have 1, 2, 3, 4, 5 on the outside. Okay, don't worry about the CO2 right now. So we have 5 on the outside. Okay, so what's going to happen here? Where's the oxygen going to go? Well, because you have 5 molecules currently on the outside, that would be my area where you have a high concentration of them. And on the inside, you only have 2 of them, so that'd be an area where you have a low concentration of oxygen. Therefore, you're going to go from the high to low concentration area. Now, this is a bit trickier in terms of, well, how much is going to be in every area if they're evenly distributed at the end? Well, let's figure out the total. So the total number of oxygen molecules would be, if we add these two guys together, that would be 7. Now, the problem is you can't take 7 and divide it in half, because if you did that, you get 3.5. You can't have half of a molecule. You need to have a whole number of molecules. So what that means in this situation is you're not going to have a perfectly even distribution. You're going to have 1 more in one area. Now, there's still going to be some molecules that move to the inside of the cell. So if you have 5 on the outside, 2 on the inside, maybe what I'd expect to happen is just maybe one of these guys goes in. So if one of these guys went in here, then you would have another O2 in here. And then what I would have is, instead of having 2 on the inside, you'd have 3 on the inside, and you'd have 1, 2, 3, 4 on the outside. Okay, so I still had motion of molecules from high to low concentration area, except there wasn't a perfect even distribution, because if it's an odd number total, you can't split it in half. You can't have half the molecule. Okay, so that's for the O2. How about for the CO2? So let's focus just on the CO2 molecules. So I have 1, 2, 3, 4 carbon dioxide molecules. So I have 4 on the inside of the cell. How many do I have on the outside? 0. Okay, so on the inside of the cell, because you have 4 carbon dioxide molecules, in relation to carbon dioxide, that would be my area of high concentration. And on the outside, you have none, so that's an area of low concentration. So the CO2 molecules are going to go from a high to low concentration area. Okay, so what's that split going to look like? Well, 4 plus 0, the total is 4. That can be split directly in half. So maybe this one and this one move to the outside. And if they move to the outside, you then have a CO2 here. You then have a CO2 there. And then you would then have 2 on the inside, 2 on the outside. You've kind of reached this equilibrium state where you have the same number on the inside and the outside. Okay, so that's what diffusion is. Diffusion is just going to be the movement of molecules from a high to low concentration area until you're as close to being evenly distributed at the end. There is another word, or another term, osmosis. Now, osmosis is just a special type of diffusion. Specifically, osmosis is the diffusion of water molecules. So I could define osmosis as being the movement of water molecules from an area of high to low concentration. From an area to high to low concentration. So if we had, again, just draw two boundaries here. Okay, so this is area 1, and we have like area number 2. We'll say that we have two water molecules in here, 0 on area 2. So osmosis would be the diffusion of water. So that means you'd have the movement of water molecules from a high to low concentration area. So if we move them around there, then get rid of this guy. He's now in here. And then until you have about the same number of molecules. So again, osmosis is a special type of diffusion, specifically the diffusion of water. Okay, so now that we've talked a little bit about how diffusion and osmosis works, we're going to focus on how water actually transports throughout a plant. We'll first of all look at, okay, well, where does water enter a plant? Water enters the plant through the root hairs. If you've ever dug up like a plant, you've probably noticed that there's a bunch of like little tiny little tangles off of like the main stem. It's like these little tiny like hairs. Same here. You got like a bunch of little tiny, very, very tiny hairs. Those are what we call root hairs. Root hairs are what we refer to as being differentially or selectively permeable. What that means is they only allow certain materials to enter. There's actually 3 ways we can describe like a material. We can say that it is permeable, permeable means it would allow all materials to enter. That might not necessarily be a good thing because there could be like some harmful chemicals in the soil that we don't want the root hairs to absorb. So being completely permeable, maybe not the greatest thing. We also have impermeable. Impermeable would be no materials are allowed to enter. Now, that would also be bad because then the plant's not going to get the things that it needs. It wouldn't get any water. So kind of like in between these two is what we have a differentially or selectively permeable membrane. So only certain materials are allowed to enter, the ones that the plant actually wants. So what does the plant want? Well, it wants water, and water gets absorbed through osmosis. So if you like water the area around a plant, what you would have is, so I'll draw a little bit of water here. Okay, so a ton of water. So why does the water go into the root hairs? Well, the ground would be an area where you have a high concentration of water, and inside the root hairs would be a low concentration area. So through osmosis, you're going to have water molecules go from the high concentration area, which is the ground or the dirt, into the root hairs. So water gets absorbed through osmosis. Again, osmosis is just the diffusion of water. The other thing plants want to absorb are nutrients, fertilizer. So I think there's like, don't quote me directly on this, but I think a lot of fertilizer bags, if you ever look at like a bag from like a garden store, it has like 3 numbers on it. It could be like, again, I'm just gonna make these up, like 14, 7, and then I think like maybe 8 or something. I feel like it tells you like proportions of like a certain amount of element, like certain like nutrient the element wants. I think the elements are phosphorus, nitrogen, and potassium. So basically, these numbers tell you how much of each there is. I'm not sure which is which. I feel like the first number is the amount of nitrogen. The next one is phosphorus, and then the third one is potassium. But I might be completely wrong in that. But nonetheless, like those fertilizer bags are just telling you proportions of like certain nutrients. And I said the nutrients are absorbed by diffusion because diffusion would just be the transportation of molecules from a high to low concentration area. So you put a bunch of fertilizer into the dirt. So let's just color the fertilizer with like purple. So you have a lot of it on the outside of the root hairs. So that would be an area of high concentration, not so much in the root hairs. So you're going to have the nutrients go from the high concentration area, which is in the dirt, to the low concentration area inside the root hairs. And then the plants get both water and they can get some nutrients. Okay, that's how they enter the plant. You probably have noticed too that if you look at the root hairs, there's a lot of them. The reason there's so many of these root hairs is by having a lot of root hairs, it increases the surface area of the root hairs in contact with like the environment. And if you have a larger surface area in contact with the rest of like the ground or just the surrounding environment, a larger surface area means you can actually absorb nutrients and water at a much larger rate. So that's why we see so many of them. It's all about getting a large surface area. Exit. So how does the water leave the plant? The water leaves the plant at the leaves, specifically on the underside of the leaves through a part of the plant that is called the stomata. What is a stomata? It's kind of like just a little opening. I mean, if you look at the illustration that we have here, it almost looks like a mouth. Like you can think of like here's like some like the lips, and like there's a little tiny gap here. Okay, so this little red gap, it's like an open mouth. Okay, so if the stomata is open, then water can leave. If the stomata is closed, it cannot leave. So how does it exit? Well, the stomata is open during the day, and then you can lose water through transpiration. Now, in terms of what transpiration is, we talked about this briefly in the Interactions and Ecosystems unit. Transpiration is specifically the vaporization Vaporization is a phase change where you go from having a liquid to a gas. And it's specific to plants. So how does the phase change occur? Well, this is why the stomata is open during the day. During the day, it's warmer outside, so any water in the leaves would then heat up. And if they heat up, there could be a phase change from a liquid to a gas. So then the water turns from liquid water into water vapor, and then it can escape the plant. Well, how about the movement in the plant? Like, how do you get the water from the root hairs all the way up to the leaf where you have the stomata where the water can leave? Water moves from the root hairs to the leaves through a part of the plant that is called the xylem tissue. You can just think of the xylem tissue as being like a large canal. So maybe I'll sketch a really poor picture here. Okay, so let's do, let's say we have our root hairs. Okay, so there's a bunch of root hairs here. Think of the xylem tissue as being like just this large vertical straw, okay, that's inside the stem. Okay, so just a big straw here. Big straw. Okay, so these are my root hairs. Okay, this big straw that goes from the root hairs all the way up to the leaf. And again, I can't draw a leaf, but I'll try. Does that look like a leaf? Not really. It's more like a, oh my goodness. The more detail I add here, the worse it's getting. That's supposed to be a leaf. Okay, let's just write down leaf. Okay, and on the underside of the leaf, you have the stomata. Okay, and this straw, or this canal that connects the root hairs to the leaf, we're going to call that the xylem tissue. So what exactly does the xylem tissue do? It's this canal that just simply moves, or this channel that just moves water and nutrients from the roots up to the leaves. Okay, so it just brings it straight up here. Okay, now I have one question before I just end the lesson. So how do you get the water up there? So the problem is you need water to work against the force of gravity. The force of gravity wants to pull the water straight down. So you need to actually bring the water up this vertical height. So you're going to have to work against the force of gravity. So how can this actually occur? Well, there's two reasons behind this. Okay, so for example, let's say that the root hairs absorb some water, and we'll just draw a little bit of water inside of the straw, okay, inside of the xylem tissue. Okay, a little bit of water is in here. Okay, so how do we get this water up to the leaf? Okay, again, it has to work against the force of gravity. Well, let's say we watered the ground again. Okay, so we put a bunch more water inside the ground. Okay. In fact, there's more water inside the dirt, and the water in the dirt is an area of high concentration of water. Well, what happens if the ground is an area of high concentration of water and the root hairs have a lower concentration? Well, you're going to have the water move into the root hairs. Okay, so this water is going to go into my root hairs. It's supposed to be arrows pointing towards the root hairs. Okay, now, if water goes into the root hairs, what's it going to do to this water that's already sitting in here? Well, if you bring more water into the xylem tissue, what it's going to do is it's going to take this water and it's going to push it up. So the more water you absorb, all the new water is going to come in here, and it's going to just basically, let's see if I can draw some arrow. Okay, through the root hairs, the new water is then going to come to the bottom of the xylem tissue. And then it's going to displace the already existing water further up. So up it goes. So that's one way you can actually get the water from the root hairs all the way up to the leaf or the stomata. Now, there is another way as well. Okay, so when the water leaves the stomata through transpiration, okay, so again, it leaves like the underside here. You can think of it as kind of like this vacuum effect. So as the water through transpiration starts to exit the stomata, what it does is it starts to kind of like tug on the water in the xylem tissue. So again, all these molecules of water are leaving through transpiration, and then as it leaves, it kind of like pulls on the water in the xylem. So it also pulls it up. So there's a couple things happening here. There's pushing of the water. The pushing of the water is from absorbing new water through the root hairs, and then new water pushes the water further up to the xylem tissue. And you also have this pulling effect. So as like the water molecules are leaving the leaf through transpiration, again, I said there's kind of like a little bit of a vacuum effect where they start to pull on the water in the xylem tissue and then pull it up even further. So in a nutshell, this is a very basic explanation as to how this is working. That is how water enters a plant, moves through the plant, and then eventually exits the plant. Okay, that's it for today's lesson. And then I believe in the next one, we're going to talk a little bit more about photosynthesis, respiration, and specifically gas exchange inside of plants. As for today, we talked about water movement. And I'll talk to you in that lesson.